Next, we'll use our knowledge of differential equations to develop a model for population growth in which there are no constraints. So let's assume that we have a population whose size can be represented by a function p that tells us how much population we have at given time t. And if the population grow or decreases, or it can remain a constant, but since we have a function, that function will have a graph, and as the population changes, so here at time t we have a population at time t, and as the population changes, the quantity represented by this function, or we can also write it using Leibniz notation, this quantity is what we would call the rate of growth. So basically dp dt tells us how fast the population grows. However, if it declines, then we can call it the rate of growth, so let's just call it the rate of change. And if it's growing, we'll call it the rate of growth, and if it's declining, then we would call it the rate of decay. And if we assume that there are no constraints in terms of how much population can grow, so no constraints means population will keep growing as long as you allow it to grow. So it will grow like this. Well, it will continue to increase, right? So now the question is, how fast does it grow? And usually in nature, it has been observed that the rate of growth, so it's like the law of nature, when you have infinite supply and no constraint, then the rate of growth we say is proportional to what? Well, it's proportional to the size of the population. So the larger the population, the faster it will grow. So it seems pretty natural. Again, if you only have like two representative of some species, these population won't grow as fast as when you have 2,000 representatives of some species. However, the question here is, how do we express this mathematically? So mathematically, we express this as, hey, this is my rate of growth. The size is expressed by a function p. And in algebra, we use this symbol, like I'm just going to draw it as a squiggle line, but this will stand for what we call varies directly. So varies directly, or being proportional to some quantity, it's the same thing. And in algebra, we have learned that when two quantities vary directly or said to be proportional, they can be expressed mathematically as one equals to the other one multiplied by some constant. And that constant is called the coefficient we can call it the coefficient of variation, or let's just call it the coefficient. It's some unknown coefficient that will vary from population to population. And now that we expressed this law of nature mathematically, and if we just pause there for a second and take a deep look, what do we actually have over here? What we have is a differential equation, and it's not just a differential equation, it's of a certain type that we should be able to recognize. It's actually a separable differential equation, and as such we should be able to solve it. So how do we solve separable differential equations? We separate the variables, so I'm going to move the p to the left. I'm going to move dt to the right. Again, it looks like I'm multiplying, but I'm not. But none of this makes sense until I throw the integral in there, and this is exactly how we produce the solution of this differential equation. And we're going to solve it by just integrating both sides. And to ease the notation, I'm just going to remove that p of t. So here we're going to treat p as just a letter that represents a function, but on the left hand side it's just now became a variable of integration. So on the left hand side we have a ln of absolute value of p, and on the right side we have kt, and at some point we have to put the constant of integration, and we have seen this before, so we're gonna have multiple constants here. So let me throw an index 1 over there, and if we assume that p, the population, is positive, then we don't need the absolute value in there, because when p is positive, absolute value of p is same as p. So the next thing we're going to do is we're going to exponentiate both sides. So we're going to write e to the power ln p is equal to e to the power kt plus c1, but using the laws of exponents, we can bring the c1 to the front. So according to the laws of exponents, this is true. So we're going to have on the left side p, and on the right side we're going to have e to the power c1 times e to the power kt. And if we let e to the power c1 be our c2, and since it's going to be our last constant, let me just call it as c. So finally we get the following solution of this differential equation. So p of t is equal to c times e to the power kt. And we can make this initial value problem by adding an initial condition. So for example, if p of 0 is expressed as p0, then we can use this and find c. So to find c, we're going to plug in 0. So on the left we have p0, on the right we have c e to the 0. So that means c is exactly the p0. And now we have the solution for the initial value problem. So this is the solution. So if we have a population that grows without any constraints at the rate proportional to its size, then this is what we call the unlimited growth model. then the population at time t can be expressed in the following way. So normally, it's okay to use k as the coefficient of some sort in algebra, but in this class we're going to use r as the coefficient of growth, and there's a reason for that. So r will stand for the rate at which the population grows, and in this case we're going to call it the rate of continuous growth. So continuous here as the opposite to discrete growth, where growth only happens in discrete steps. So here we have the rate of continuous growth, and P0 is the initial population. So initial here refers to t equals 0. And when r, the rate of continuous growth, is positive, then we do have actual growth. And when r is negative, then we have decay. So again, we still call it unlimited growth model, but when r is negative, then growth becomes decay. And let's do an example. Let's do a problem. So in this example, we have the natural growth model, which is synonymous to the unlimited growth model, and everything is given. So if we carefully read the problem, we'll be able to plug everything in. So here's the function that we're working with. Just write it right here. We don't have to solve this differential equation over and over because we recognize when it's applicable, and then we can use the knowledge of the problem to plug in the parameters into the answer instead of solving it again. So here the initial population is 10,685 e to the power r. So r means here, r being positive means the population grows, and we put t over here. So this is our model. Now we have the model, and if you do have the model, if you don't have to solve for it, then it basically becomes just an algebra question. So find the number of bacteria in a colony after t equals 2 hours. So they're literally asking us to evaluate p of 2. So we throw these numbers into the formula, and I'm going to use a calculator, or maybe throw it in Wolfram Alpha. And the answer here is 11210 something, but it's asking us to round to the next highest integer, so I'm going to round this up, and this is my answer. So there will be this much bacteria after 2 hours. To answer the question in part B, again, we already have a model. So to find how many hours will it take for the population to grow to 20,000, we have to solve this equation, which is nothing but algebra. So we set up this. equation, and t will be equal to ln of 20,000 divided by 10,685, all that divided by 0.02. So again, I'm just gonna use Wolfram alpha. We're gonna put ln 20,000 divided by 10,685, all that divided by 0.02, and the answer is 31.3. Oops. Did I say 31.3? 31.3. But we have to round up to the nearest integer, so the answer will be 32. And what are the units here? T is measured in hours, so it will take 32 hours to grow this much. So unlimited population growth model, it's pretty simple, and we have basically done all possible exercises that one can think of when it comes to this type of growth.